Okay, so in this lesson we're going to be learning about direct variation. In our next video we'll be talking about inverse variation. So these two kind of go together. They're just opposites of each other. So it's really important to make sure that you get these definitions down, especially for direct variation. So make sure everything that's highlighted in yellow, if you're not following along on my notes, that you get that stuff written down, because that's going to be really important. So let's talk about direct variation today. It says an equation. Direct variation is where we have an equation in which as one variable increases, the other variable also increases. Or the vice versa is also true. So if we have a situation where as one variable decreases and the other variable also decreases, that too is an example of direct variation. Let's look down for a second at this direct variation function down here. So here it says a direct variation is going to be in the form y equals k times x to the nth power. Now let's talk about k for a second. K represents the constant of variation. That's the non-zero. That's what this is saying. That k is not going to be equal to 0, so it's a non-zero constant. It's a number. Okay, that's going to be true for any scenario using that equation. And the other thing too is that your exponents are all going to be greater than 0. Now some terminology is when we say something varies directly, we can also say that y is directly proportional to x to the n. Now an example of direct variation is the formula for the area of a circle, pi times the radius squared. Pi in this case is going to be your constant. Anytime we try to find the area of a circle, we're always going to be using pi times the radius squared. The radius can vary, but the pi won't. The other thing too is this. If you didn't know this was an example of direct variation, you could figure it out, because if you think about it, as your radius increases, the area of the circle is also going to increase. So if you have a small radius, that's going to result in a small area. If you increase the radius, that's going to result in an increased area. Let's look at this example now. In these notes, what we're going to do is we're going to start out by going through some of these problems in what I would refer to as baby steps. We're going to take it step by step by step. When really, this whole problem that you see that takes up this entire screen right now, the steps to do that is going to be the same as these last two examples we're going to look at. So we're going to start out, like I said, working through this using baby steps. So let's first read the problem. It says the volume V of a regular icosahedron is directly proportional to the cube of the length L of an edge. And we're going to write an equation. The first step here in part A is to write an equation. First off, if I just read that, the volume of a regular icosahedron is directly proportional to the cube of the length of an edge. If you didn't know one little trick, it's going to make setting up an equation really difficult. But here's the trick, because we know all the way back to middle school, you learn little words, little phrases that represent symbols in math. Like is one of them. Is would represent equals. Of means times. But here, when you see this phrase is directly proportional, I want you to recognize that as being equals k times something. So every time you see varies directly or directly is proportional, it means equals k times something. So now we're on the road to setting up our equation. So our equation here is going to be the volume is directly proportional. So it's going to be V equals k times something. And it's directly proportional to the cube of the length L. So I'm going to write that as L cubed. Now I refer to this as what we call the general equation. Because here's a diagram of an icosahedron. I also have one of these hanging up in my classroom. But if we wanted to find the volume of this icosahedron, right now I could not find it using the formula that we just found, because I don't know what k is. Remember, k is not a variable. K is a constant. K should be a number. So before I can find the volume of this icosahedron, I need to have a specific equation. So I need to find out what k equals. That's our next step. So to find out what k equals, we need to know what, if I know a value for V and a value for L that I can plug in there, I can use those to find out what k equals. So let's look at this next part. It says a regular icosahedron with an edge length of 4 centimeters has a volume of about 140 cubic centimeters. Determine the constant of variation k. So that's going to be my next step to find out what k equals. So I'm going to plug 4 centimeters in and the 140 cubic centimeters in. Now note about this, we really need to only plug in the 4 and 140. Just at the units, give you an idea if you didn't see some of the other stuff that would tell you where to put it, that anytime we have volume, it's measured in cubic centimeters. That's why the centimeters cubed are there. So I'm going to put that in for my V, so it'll be 140 equals my K. My length is measured in just plain old units, so this will be 4 centimeters. And my volume, or my length, is going to be cubed, so it'll be, in my formula it says L cubed. So now I just solve this. So 4 cubed is 64. So to find out what k is, I'm going to divide both sides by 64. Now when you do this on your calculator, you get 2.1875. Now note about rounding. This is really, really important. A lot of times the problems will say, round your answer to the nearest tenth, round your answer to the nearest hundredth. Well, really, with this particular problem, our goal is to actually get to part D. That's what we're trying to get to. That's what we're trying to find. When we're on our way to that goal, you never want to round. At least, you don't want to round close to the decimal. Sometimes you'll have a decimal that'll run on your calculator. The closer to the decimal you round, the more inaccurate your final answer will be. So if I rounded this to 2.2 or 2.19, it's going to throw off my answer. Even the slightest bit sometimes can throw your answer by as many as 10, 15 units. So you want to make sure that when you're doing these problems, when we're in the middle of a problem, don't round close to the decimal. The further past the decimal, the better. I like to use a rule of, instead of saying a rule of thumb, a rule of hand, you have 5 fingers. So as you're working way to the final answer, use 5 numbers past the decimal, and usually then you'll be pretty accurate. But this one, we'll just leave it as 2.1875. So that's your second step. So going back, our first step was to come up with the general equation. Our second step was to use the 2 numbers they give us to find out what k is. Our third step is really simple. We're just going to take our answers from parts A and B and combine them. We're going to write a single variation equation is what they call it. So the variation equation is more of a specific equation. Where instead of using V equals K, we're going to actually use the value for K that we found. So it's going to be V equals 2.1875 times your length of the edge cubed. So now if I wanted to find the volume of any icosahedron, including the one in my classroom, I could just measure the length of one of the sides, plug it in here for L, and I could get the volume. So in part D it says approximate to the nearest cubic centimeter the volume of an icosahedron with an edge length of 5. What I'm going to do is I'm going to put 5 in for L. And when we do that, now here they say round to the nearest cubic centimeter. That means we're not going to have any decimals. So we'd round this to be about 273 centimeters cubed. Okay. We're going to look at another example, but again, I want to show you, so this took us through in baby steps. Our goal is to figure out the volume when we knew the edge length was going to be 5. Let's look at the last problems. So in 2a there, it says, suppose b varies directly as the 6th power of g. If b equals 729 when g equals 2, find b when g equals 10. So the 4 steps that we just did, we're going to use to solve this one when we get to it. But let's look at one more before we do that. Here it says, the surface area S of a cube is directly proportional to the square of the length E of an edge. Now, as we go through this problem, what I want you to do is I want you to try each step. So I want you to, we'll read part A here together, but I want you to pause it, and I want you to try to set it up, and then hit play and make sure that you get it correctly. And do that for each part, because I want to make sure that you're understanding this. And I want to make sure you're getting feedback right away. So let's look at part A. So it says we're going to write an equation. So again, it says the surface area of a cube is directly proportional to the square of the length E of an edge. Here, so why don't you guys pause this? Remember that phrase is directly proportional. and write a general equation here for this problem. Okay, you should have gotten, remember, directly proportional means equals k times something, so it's going to be the surface area, S equals k times, now this says it says it's the square of the length, E, so I'm going to say times E squared. Okay, now let's look at part B. It says a cube with an edge length of 5 has a surface area of 150 square centimeters. Determine the constant of variation, where that's your value for k. So why don't you guys take a minute and use that information to find out what k equals. So pause the video now. Okay, here's what you should have gotten. You should have gotten, well, not S, you should have gotten 150 equals k times 5 squared. When you do the math, you should have gotten k equals 6. So now part C, why don't you set up the equation and pause the video. Okay, you should have gotten S equals 6 times E squared. Okay, now use that equation to do part D. Okay, what you should have done, put 8 in for E, so it'd be 8 squared, or 64 times 6, which gives you 384. Here we're dealing with centimeters. We're trying to find the surface area, so it's going to be squared. Anytime we deal with area, it's square units. Volume is going to be cubic units. Okay, so all of these first two examples that we did followed these 4 steps. And these are the 4 steps that we're going to use for all of these problems now from here on out. Because they're not going to walk you through, they're not going to handhold you here. You're going to have to know how to do these on your own. So the first step, you're going to write out a general equation. What I mean by that is you can have it in the form y equals k times x to some exponent. And again, you won't always use x and y, we're just using this as a template, so to speak. Like in the previous problem, we used v in place of the y, and we used e in place of the x. Second step, we're going to find out what k is. They're going to give us 2 numbers, plug those in, figure out what k would be. Third step, we're going to combine those first 2 to create a specific equation, or what they call a variation equation. And the last step is you're going to actually answer the question they're asking. You can evaluate the function to find the missing value. Okay, so what we're going to do is we're going to stop the video here because I'm limited to making videos in 15-minute chunks. So watch the second video to see how to do these next 2 equations.